Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. Want to discuss with you some really, uh, to me, exciting developments. As you can see here, and this has appeared in phys.org/news, April 14th edition, ocean temperature reconstructed over the last 700,000 years. So what we see here is a nice photo of a mass spectrometer at the University of Bern. It was this very machine that was used to help reconstruct ocean temperatures for the last 700,000 years. So researchers from the Oeschger Center for Climate Change Research at the University of Bern reconstructed for the first mean ocean temperatures over the last 700,000 years using ice core data. The new knowledge serves to improve our understanding of the climate system. Bern's ice core researchers were already able to demonstrate in 2008, 13 years ago, how the concentration of CO2 in the atmosphere has changed over the past 800,000 years. Now, in the intervening 13 years, sampling, measurement, analyses have improved, especially the equipment and the technology, that we are able to get proxy data all the way back to when that big rock came tumbling out of the sky at the end of the Cretaceous period. And we're now able to reconstruct CO2 and temperature, and therefore, by implication, climate for the past basically 60 million years or so. Now, using the very same ice core from Antarctica, the group led by Bernese climate researcher Hubertus Fischer shows the maximum and minimum values between which the mean ocean temperature has fluctuated over these past 700,000 years. The results of the reconstruction have just been published in the journal Climate of the Past. Here are the key findings. Mean ocean temperatures have been very similar over the last 7 ice ages, averaging about 3.3 degrees C colder than pre-industrial reference period. This is already further suggested, further supported by analyzing deep water, reconstructing deep water temperatures using marine sediments. You can get a lot of information from sediment cores and ice cores. You can, looking at the trapped gases, you can measure their levels, concentration. You can use isotopic fractionation to reconstruct the past climate. You can tell, when the thermohaline circulation was flowing or not. You can look at the various elements in the marine organisms, radiolarians, foraminifera, and so forth. Diatoms. Diatoms are big, widely used as well. However, ocean temperatures in the warm periods 450,000 years ago were much colder, and CO2 concentrations were lower than in our present warm period. Okay, let's kind of, what they're saying here is that if you look at the ocean temperatures from the last 7 ice ages, those ocean temperatures were colder than the interglacial periods 450,000 years ago. But when you look at the ocean temperatures of that interglacial period from 450,000 years ago, those ocean temperatures were colder than today's ocean temperatures. And the CO2 concentration were lower than today's CO2 concentration. So I want to make sure I want to clarify that so everyone's clear on that point. Despite similar solar radiation, what does that mean? That means the conditions of the Milankovitch cycle were about the same as they are now as they were 450,000 years ago. In other words, the tilt of the axis is about the same. The shape of how elliptical the Earth's orbit is about the same. Where the Earth was in its orbit when the solstices and equinoxes occur was about the same. The new measurements show that ocean temperature is also shaped by changes in ocean circulation. Let me repeat that again. The new measurements show that ocean temperature is also shaped by changes in ocean circulation. I just did a video on ocean heat content where I showed you the data and I gave you my analyses of the data, where basically I am seeing evidence that the thermohaline circulation is slowing down, and we're also seeing a very pronounced stratification of the upper 500 meters. When you have the thermohaline circulation flowing, that is a way for not only CO2, but heat to be sequestered from the surface down to depth. If that circulation slows or stops, that sequestration does not take place. You then start concentrating, you start accumulating massively the heat and the CO2 in the upper layers of the ocean. We're starting to see that. Keep in mind also that gas solubility decreases with an increase in water temperature. So, as the water temperatures continue to increase, the ability of the ocean to absorb CO2 will decrease, thereby leaving more CO2 in the atmosphere that will further warm the planet. Continuing to warm the oceans, you will get to the point where the gas solubility is saturated, knows at maximum. That's when you cannot absorb any more gas, and then continuing past that level, the gas that is dissolved in the ocean will outgas, will come out of solution and go back into the atmosphere. This includes all gases and includes CO2, methane as well, thereby even further warming the atmosphere. And now you can see you create this little runaway system because you're going to increase the CO2 because the oceans can't absorb it, and then you're putting it back into the atmosphere from the ocean. So those who say that, getting rid of emissions will solve the problem, they're wrong. Most people just look at the atmosphere. You want to know who the real driver of climate change is? The real driver of the Earth's climate is? It's the oceans. The oceans drive the climate. And we're collecting the data that's now telling us what the heat distribution was like in the past. The so-called global circulation of deep waters has a significant impact on heat storage in the ocean. And I discussed that with you in my ocean heat content video. Basically, if you can sequester the heat, you're doing okay. If you can't, you're not doing okay. Now, to understand how the climate system's heat balance is changing, said Dr. Fisher, we have to understand the ocean first and foremost. That goes back to what I just said, that the oceans are the driver of the climate. For example, and this is what I stressed in my ocean heat content video, 93% of the additional heat that humans accumulate by increasing greenhouse gases is currently stored in the ocean rather than in the atmosphere. If the oceans can no longer absorb CO2 because of solubility is maxed out, that's CO2 stays in the atmosphere. And as I just said, you keep warming the waters, you're going to then start putting the CO2 in the oceans back into the atmosphere, further increasing ever more so. So those models that are now saying, well, we could see a temperature rise of, minimum 5 to 7 C, probably 7 to 9 C, maybe even 9 to 11 C by 2100. It is not far-fetched. They're looking at this. They're taking that into account. Plus, the added heat in the atmosphere will further thaw the permafrost, further releasing more methane, continue to warm the oceans. You will then thaw and melt hydrates, further releasing more methane. You're creating a massive runaway system. in such a short period of time. This means without the ocean heat uptake, temperature increase measured on land would be significantly greater. Right, that's what I just described for you. However, because the oceans have a huge mass compared to the atmosphere, the temperature changes measured in the ocean today are very small. But let's not forget the specific heat aspect of water. It takes considerably more energy to heat up the same volume of water than it does the same volume of air. And when you think, 93% of that heat that we put into the atmosphere has gone into the oceans, and then you consider that the absorbed amount is over in excess of 200 zettajoules, that is a significant quantity of heat energy we put in. Here's a picture of an ice core from Antarctica. The relevance of data from the ocean for climate research is demonstrated by the International Argo Project. This is a mobile observation system for the world's oceans, from which, for example, continuous temperature measurements down to a depth of 2,000 meters have been carried out since 2000. These buoys, basically they have drifting buoys, about 4,000 of them. They're also measuring other parameters in addition to temperatures. So they could be looking at concentrations of nitrates and phosphates, CO2, etc. So as I just said, they got 4,000 drifting buoys that are basically all over the oceans taking these measurements. So this makes the approach of the researchers at Bern all the more astonishing comparison. We only need a single polar ice sample in our mean ocean temperature measurement, said Dr. Fisher. Of course, we are nowhere near the accuracy of Argo, but we can look further back into the past than Argo. Now, key point here, they're looking at ice cores from Antarctica. They're not looking at frozen seawater. So they're looking at the air bubbles trapped in Antarctica's glacier ice. Okay, so we need to make that, which, considering how thick the Antarctic ice is, it will give you information at least 700,000 years into the past, and of course much further. So that's what they're using to make their measurements and then to ascertain what the ocean temperatures were going back in time, 700,000 years. Now, this is the part that I found really fascinating. Usually when you get the ice core, you're looking at the O2 and the CO2 that's trapped, those gas bubbles. You look at the isotopic fractionation. You then say, oh, we had more ice on land than in the ocean, vice versa. Using isotopic fractionation, you can tell that. You can tell when the thermohaline circulation was on or off. You can tell all these things. And then using the CO2 concentrations, you can reconstruct the temperature and so forth and so forth. And I explained all that in my isotopic fractionation video. You may want to go check that out if you haven't viewed that already. But this is what these guys did, which is just like really cool. They analyze what's called the noble gases, argon, krypton, xenon. They also looked at molecular nitrogen, N2, but nitrogen is not a noble gas. The reason why they call them noble gases is kind of an old term. It's basically these gases are found at the end of a periodic row, and they have a full potential possible complement of electrons in all the orbitals and energy states, so that they're not very reactive. They don't tend to form ions, be it cations or anions. So the kind of inert, not very reactive. But you do find them in small amounts in the atmosphere, and you can find a small fraction that's dissolved in the ocean. How well each gas is dissolved in seawater depends on the ocean temperature, right? It goes back to what I said earlier. Increased water temperature, gas solubility decreases. Decreased water temperature, gas solubility increases. So you're looking at the relative levels. And from that information is how they're able to reconstruct the past mean ocean temperatures. So the prerequisite for this method are high precision measurements using a very accurate machine. And the mass spectrometer, whose photo I showed you earlier, is the very machine that they used to do this. So there are a whole bunch of people involved with that. Past ocean temperatures are determined to within 0.4 degrees C in Bern. So that's basically the level of accuracy. The precision makes it possible to trace the climate changes, warmings and coolings of the past, since the difference in mean ocean temperature between the ice age and the warm phases over the past 700,000 years is about 3 degrees C. And Scripps in the U.S. is the other team that also is carrying out such measurements, because they also have a very accurate, precise mass spec. Now, when you think about the specific heat content of water, when you think about how much volume the oceans have in a mass, 3 degrees C is a significant change between glacial periods and interglacial periods. And then when you factor in how much added warmth that we have added to the atmosphere and how much the oceans have warmed up since, get an idea of just what we're doing and the difference between interglacial periods of the past, glacial periods of the past to the current. And then you couple that to what we're seeing with the energy in the oceans, what's going on in the atmosphere. You can see that was basically putting in place a good runaway system. As I said in that ocean heat content, I'm seeing evidence that the thermohaline circulation is slowing. I'm seeing increased stratification of the upper 500 meters, which means that the distribution and sequestration of heat will not proceed as it has been, so that eventually the gases will stop being absorbed by the ocean. So those levels increase in the atmosphere. The oceans will outgas what already is dissolved at some point in the near future, most likely, further increasing gas concentrations, and therefore the temperatures that go with it. So I wanted to share this with you, a new methodology that is helping us to better understand how current conditions compare to past conditions, and then using the past conditions, we can better project what the future will hold for us. So thank you for your time. We'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.